So good morning. I am Krishna Kumar. So we continue with our lectures on analysis on Rn. We started looking at the structure of Rn and still have some more things to consider before we take up linear transformations. So where did we stop last time? What we did was this dimension of Rn equal to n. This we proved. Just recall how we proved it. We proved that any set of k vectors for k strictly less than n do not span even if these set of vectors are linearly independent. So in short, we can say that if you choose k vectors x1, x2, etc., xk, which are linearly independent also, where k is strictly less than n, then it cannot span Rn. Also, we observe that any set of k vectors for k greater than n is linearly dependent. Now put these two informations together. So what we are going to say, we are searching for a basis. What's a basis? A basis is a set which is linearly independent as well as it spans Rn. So you see that what you can say from the first one. The first one says that any basis will consist of more than n elements. So the first one that any basis for Rn has more than n or more elements, because the basis has to span the whole space. Secondly, from 2 we infer that any basis has n or less number of here we are using the fact that n, every basis is linearly independent. So here we use basis spans. Here we use basis is linearly independent in R. So we put these two things together, then it follows that the number of elements together basis being a linearly independent set that spans Rn has exactly n elements. So that is the way in which we have concluded that this has exactly n elements. Now that involves proving these two statements. Okay. Now I leave it you to prove this, but let us explore this problem. So you take the case R. Let us take 3 vectors x1, x2, x3. Then what we claim is that dependent. So what you want to show is that it cannot be linearly independent. So I look at this one. So if not, C1 x1 plus C2 x2 plus C3 x3 equal to 0 implies equal to 0. Okay. Now what does that mean? x1 has 2 components, x2 has 2 components, x3 has 2 components. So C1 into 1 1 0. What does this mean? This means two equations. C1x11 plus C2x21 C3x31 equal to 0. C1x12 plus C2x22 C3x32 equal to 0. Now you see that this is for determining C1, C2, C3. These are the unknowns. To determine these three unknowns. And there are two equations. So it's an underdetermined system. Being an underdetermined system, this has always a non-trivial solution. Okay? It has always a non-trivial solution. Of course, it has a trivial solution, namely C1 equal to 0, C2 equal to 0, C3 equal to 0 is always a solution. But being a underdetermined system, namely there are two equations for determining three unknowns, this has always a non-trivial solution. So there are three equations. Two equations to determine three unknowns. Okay. Therefore, you have C1, C2, C3, not all of them 0, such that C1x1 plus C2x2 plus C3x3 equal to 0, which means x1, x2, x3 is linearly dependent. Now you can improvise this argument to R. Okay? Right? Now if you choose a non-zero vector x, there is just one vector. Okay? Then Cx, as long as it's a non-zero vector, it's linearly independent. But two vectors may be linearly independent. That's also possible. Okay? So you see that Cx non-zero vector. Okay. Now you have and this does not span, so x1 not equal to 0 does not span R2. Why? Because you let y belong to R2. Okay. Given x, what do you have? x1 cx1 equal to y. That's the Taylor solution. So this is conditional. So what you have, cx1 1 equal to y1, cx1 2 equal to y2, where y is given to be arbitrary. So this determines, essentially, if x11 is not equal to 0, then this determines the first equation. So if x11 equal to 0, then y11 equal to 0. So that restricts the class. So if x11 is not equal to 0, then this determines C. And for that C, y2 may not be, x12 may not be equal to y2. So that's the problem. So you see that this is how you work on it. Now you try to improvise the same type of argument for the general R. Yes. Now we equations of you recall, in the case of R3, we said the subspaces are lines through the origin and planes through the origin. This is a line, and then of course you have planes through the origin. So you have two vectors given here. So here there's a third vector. So if this vector is A, then it is TA, the whole lot. Okay. Therefore, now we see that let then you see that, then what do you have? Then this means K is certainly less than or equal to N. That we already have. Right. K is less than or equal to N. Now, look at the span of K. This is actually the setup for X, for which X is equal to P1 Pk, where you have Pi belong to R for I equal to 1 . Therefore, we take X equal to P1 x1 plus etc. pk xk as the equation of the span of xk in the parametric form. The parameters are t1, t2, etc. tk. Okay, so this is in the parametric form. So if you start writing this up in the component form, we have it consists of what? It consists of this, namely T1 or let me write this in this form, Ti x I 1i okay, sigma Ti x 2i I'll write it this way. So the first component, there are n components for x because we are in R. Therefore, I think I better make some change here. One. So that there is no confusion. Therefore, this is equal to y equal to. So what happens? So y1 equal to t1 x 11 tk x k. These are the components. Y1, Y2, etc. Okay. So this gives the component wise equation for the span of x1, x2, etc. x3. There are n equations for k unknowns. Okay, so these are the constraints actually that you would have. Okay, so this is going to be the set of equations that you have. So I think maybe for clarity we will look at what happens in the case of Arthur. Just work it out in the case of Arthur. Let us take up. What are the subspaces that you have here? The subspaces are lines and planes, and planes passing through one group. So we start with the vector. Or I will use A non-zero vector. Then A equal to B3 with A1 square plus A2 square, A3 square is not equal to 0. This assures that one component, at least one of the components, is not equal to 0. So that A is not equal to 0. So this means A is not equal to 0. That's how it is expressed. Now what about the equation? The equation is going to be x equal to TA. What is x equal to TA? If you write in the component form, this is the span of A, where T is the parameter. But in the component form, what you have is x1 equal to TA1, x2 equal to TA2, x3 equal to TA3. Now this gives the equation of a line in the parametric form in R3. Okay, this is the equation of a line. Line in R3 passing through origin with direction ratios formally we have x1 by A1, x2 by A2. I want to make a caution here. See, there may be a situation where only one of this component is different from 0. In that case, you will get something like, say for instance, suppose your A is equal to 1, 0, 0. Then what happens? Then this will be x1 by 1 equal to x2 by 0, x3 by 0. So you might ask, what about division by 0? It's not division by 0. It's a statement that x1, x2, x3 is proportional to 1, 0, 0. That's all. Or it corresponds to three equations, that is x1 equal to t, x2 equal to 0, x3 equal to 0. That's the equation. You have correspondingly, this gives x1 equal to ta1, x2 equal to ta2, x3 equal to ta3. What's the meaning of that? Okay, so that's just a result. Okay, so this is not to be taken. That's why I have used the word formally. Okay, it's only a proportionality statement that we have taken. Now coming to the plane. So what you can do is, see, if you choose two vectors which are linearly independent in R3, so let A1, A2 be 2 or A comma B, two linearly independent vectors in R3. Two linearly independent vectors in R3. Now what is the parametric form of the span of the vectors A and B? See, the span of A and B, this is the span, consists of all S B G comma S belonging to this collection. Okay, so let me write this. So you have the vector equation given by x equal to CA plus SB, that is x1 equal to TA1 plus SB1, x2 equal to TA2 plus SB2. So this is the parametric form. The parametric form of the equation is given by this P comma S belonging to. This is the parametric form of this. Now what does this mean? This means, see, suppose you want to eliminate T and S between these two equations. Okay, so the equation will be eliminate T comma S between equations, these two equations. Okay, so what do you get? Sorry, you have a third equation. 3 equal to B A3 plus S B. Sorry. Yeah, S B. Between these three equations. Okay. So if you were to eliminate this, what happens is, this is what you have. You have determinant of one P of x1, x2, x3. So you have got A1, B1, A2, B2, B3. Now this is of the form where psi 1, psi 2, psi 3 are determined in terms of A1, B1, A2, B2, A3, B3. It's very easy to find out. Okay, you know that this is a plane passing through the origin in R3. Okay. Conversely, suppose you have in R3, you have a plane passing through the origin. Can you put it in this form? It's quite possible. You choose two vectors in R3. See, in this plane, suppose this is the plane P. Okay, so you choose A and B. So that A and B are linearly independent. Suppose the given equation, the given plane is origin is A is psi 1 equal to 0, where at least one side is different from 0, that is now what one does is choose A and B vectors in R3 such that psi 1 A1 plus psi 2 A2 plus equal to 0, psi 1 B1 plus equal to 0, where A1 A is not equal to A times B for any k. Okay. Right? Choose A and B I will also put A, B not equal to 0. A comma B not 0. You have such, you can find such numbers satisfying this equation. Such set of numbers can always be found. And once you get that, then the corresponding equation is this. So you write x equal to is the plane in the parametric form. So let me just give an example, very specific example where I just have this. Okay. So here psi1 is equal to 2, psi2 equal to -1, psi3 equal to 1. Now what you have to do? You have to choose A and B. That is A1, A2, A3, B1, B2, B3 such that A1, A2, A3 satisfies this equation. B1, B2, B3 also satisfies this equation. So suppose I choose x1 equal to 1. Then what are the corresponding values for x2? In fact, I can choose x3 equal to 0, x1 equal to 1, x3 equal to 0. So you have 2 minus x2 equal to 0, which puts x2 equal to 2. So the vector that I have lying in the plane is 1, 2, 0. So this is your case. Similarly, I choose x1 equal to 0, x2 equal to 1, then x3 equal to 1. This also lies on that. Therefore, B I take as 0. Now you see that both A and B, they form a linearly independent set. So what is the vector equation of this? X is equal to PA plus B. This is the equation. Okay? Or what you have is x1 equal to P A1 plus S B1, x2 equal to 2P plus S. Now you eliminate T and S between the three. What you get? So I can replace S by x3. Okay. x1 xt by x1. Therefore, I get x2 equal to 2x1 my 2x1 plus x3, or 2x1 minus x2 plus. So you know that this is a plane passing through the origin. Now I have picked up two vectors which are linearly independent and lie in that plane. And in terms of that, this representation can be given. Now, one remark I want to make is the choice of these three vectors, these two vectors, is not unique. there are different choices that you can make. This is not the only choice that you have. You can make different choices because in that plane there are several pairs of or infinitely many pairs of linearly independent vectors that you can choose lying in that plane, and any such pair would serve the purpose and give you this. So that is just on the straight lines and then this is the lines. So you get a feel for things now. Okay. Now my advice is that if you want to understand something in Rn, try to understand that concept first in R2 or R3, where you have the geometry also to give you some insight into what is going on. And this is very important. You get a geometric insight, then you understand what you mean by it. Then in the case of Rn, you will see that there are all sorts of subspaces that you can have, k-dimensional subspace you can have. Then you see a similar process with LP. Okay, right. So now I think what we have so far done is that in Rn, a set of n vectors would span Rn if and only if it is linearly independent. That's the first thing. The second statement is every basis in Rn consists of n vectors. The third statement that you have is for 1 less than or equal to r less than or equal to n, and if y1, y2, etc. yr is linearly independent set in Rn, then x has a basis consisting of y1, y2, etc. yr as a part of it. This is what we said last time. So how do you work on that? So what's the statement? The statement is this. Suppose you have x or Rn. It is n-dimensional. And you have a basis y1, y2. You have r linearly independent vectors that we choose. So this is a linearly independent. Now what we want to work on is construct a basis for Rn which will have y1, y2, etc. yr as a part of it. So how do we proceed? Start with the set S which is equal to then adjoin to this a basis. A basis would consist of n vectors. Say x1, x2, where x1 such a basis exists. For instance, you can as well choose E1, E2, etc. En. Okay, that's a particular choice that you can make, or any such basis you can choose. Now, what one does, what you do is start eliminating elements from it. How do you eliminate elements from it? Pick the first element appearing in this set which is linearly dependent on the other elements. Okay. First of all, you see that none of this. Okay. One thing that you have is that S spans R. Why it spans Rn? Because it is x1, x2, etc. xn is already a basis. So these set of vectors span. These set of vectors are some additional things that are brought into it. Okay. Now what one does is the following. You take x1. Okay. Check whether it is. So you first consider y1 check whether this is this. Independent. If it is linearly independent, then you retain this. Okay. So what you do? Then you include. So if this is linearly independent, then you already keep this one. If it is linearly dependent, then it means that x1 can be written as a linear combination of y1, y2, etc. yr. In that case, you don't need this. Okay, so have this one. Then what you do? You take y1, y2, etc. yr with x1. So x1 you drop off in that case, and then put x2 in. And check whether it's a linear combination of these elements. If it is, then you retain, then you throw it out, otherwise you retain it. Okay? So in this process can continue until you exhaust, you get n linearly independent vectors. Okay, so this process has to terminate. How far it can go? It can go up to picking up n minus r vectors from this class to adjoin to this. So that together they will make the basis for this. Okay, and you know that it has to. There has to be n linearly independent vectors because already there is a basis inside that. Therefore, you have r of them, and then now pick exactly n minus r of them and adjoin to this, you get a basis. Okay. So continue this process until you exhaust or you get n linearly independent vectors. There the problem ends. Okay, so that's it. So that's the method. For example, I just tell you what exactly you are doing. Suppose you are given, you take an apple. You have, say, y1 0. So this forms a linearly independent set. But this is not a basis for R3 because it doesn't have sufficiently many elements. Now how do you compute, how do you work on constructing a basis which has this as a part of it. So what you do is you choose 1, 1, 0. Put it this way: 1, 0, 1. Then you take your E1, E2, E3. This is a basis. This is your x1, x2, etc. Now what do you do? Check whether, first check this: 1, 1, 0, 1, 0, 1, 1, 0, 0. Is this linearly independent? Let us investigate this. So you get C1 this plus C2 this plus C3 this equal to 0. So you get the first component will be C1 0. This is equal to 0, 0, 0. What does this give? This gives C1 plus C2 plus C3 equal to 0. That is one equation. The second equation is C1 equal to 0. Third equation is C2 equal to 0. Therefore, this gives C1 equal to 0, C2 equal to 0, and therefore C3 equal to 0. Therefore, so C1 equal to 0, C2 equal to 0, and therefore C3 equal to 0. Therefore, they are linearly independent. So this is already 3 vectors which is linearly independent in R3. Therefore, it forms a basis. So you don't have to test these two any further. Okay. But if this were linearly dependent on this, then you could have tested with this and this. So, okay. So that's a beginning. So that's just a specific case to give you a feel for what's happening. Now I think I will consider linear transformation. So we have more or less completed the essentials of the structure of Rn that we need. Now we are going to do what you call linear algebra on Rn. So Rn is our working space. Okay, so we accept Rn as a working space. We take R. So we already know the structure of R. So now what we want to look at is mappings between Rn to Rn. So we have a transformation T from, it's a map from Rn to Rn. Okay. Now we also make, so what we are going to work on is linear transformations. Which means operators mappings from Rn to Rn. So T is called a linear operator. P is a function from Rn to Rn such that P of Dy and P of it is not any function that you consider, but a function with these properties satisfying these two properties. So this is what is called the linearity. So you consider a map from Rn to Rn. So you have P from Rn to Rn such that, or an equivalent form is P of C1x plus Cx plus dy equal to Cpx dy for every C P belonging to R for every x. Now clearly you see that this is well defined because T is a map from Rn to Rn, therefore Tx is in Rn, Ty is in Rn, the sum of these two vectors is well defined, so it gives you. So the image of x plus y is Tx plus Ty. The image of Cx is C times Tx. Now these are the requirements. Okay. Then you say T is a linear operator. Sometimes it's also called simply linear transformation from Rn to Rn. But linear transformation from Rn to Rn is quite often referred to as linear operator. The moment you say it's a linear operator, the range is already specified. Okay, so that's the convention that you choose. Okay. Now, one of the things that you immediately observe is this: P of 0 vector is 0. How do you get that? Because this follows from here. Okay. So T of equal to T 0 or T0 I can write as in this way, and this is equal to 0 times Tx. So that's an obvious inference from that. Another inference that you can immediately make is this. Suppose x1, x2, xn, let be a basis for Rn. Then T of C1 x1 plus Cn xn equal to C1 P x1 P xn. In fact, if you just take any element, moreover, for any set of vectors x1, x2, etc., xk, in Rn, whether linearly independent or linearly dependent, no such constraints are there. Some of them can maybe 0 also. Then you have this formula 2. So this is generally true for any linear sum. The t operating over a linear sum would just pass on into the sum. Okay? Or you can simply write t of you can interchange the summation. Now this also tells you something. What it tells you is the following. T is defined on Rn if it is defined on any basis of Rn. So what does it mean? It means that suppose is a basis for R, and let yi be defined as t xi to fix what txi is. Okay? Now t is defined on the whole space for every x. T is determined on any Rn. How is that? Let x belongs to then x is equal to c1 x1 plus cn xn, where c1, c2, etc. cn are determined uniquely. There's a unique choice. As long as x1, x2, etc. xn form a linearly independent set and spans the whole space. Since it spans the whole space, this is so, and it's a linearly independent set, therefore the constants c1, c2, etc. cn are uniquely determined. So that is a unique representation of x in terms of the basis. Now you see that Px is then P of Cixi. This is equal to sigma which is equal to, by our designation, yi defining Pxi, Therefore, you see that for any x, Tx is fixed once T is fixed on a basis. This is an important thing. Therefore, you don't have to say what T is everywhere specifically. All that you need say is that you choose some basis. On that basis, you fix this. For instance, if you know the standard basis. The standard basis is E1, E2, etc. En. Therefore, if you say what TEI is, then T is well defined. For example, E1 is the standard basis for Rn. Now define T is defined on Rn if T is defined on that is, you fix TE1, TE2, etc. TEN, then T is defined. Okay? Right? So, it is enough to say, I mean, this is a great advantage that you have for linear transformations. And if the transformation is not linear, then this doesn't work at all. Okay? This advantage is there only if your transformation is a linear transformation. Okay? If it is just a map from Rn to Rn, which is not necessarily linear. For instance, something like Tx given by what? Okay. Okay, if T is not linear, then this statement does not work. So it's important that this statement is valid. So once T is a linear transformation, fixing it on any basis will fix the linear transformation on the whole space. So this is an advantage that you will make use of many times. So I think I will stop here for the day and then continue with it in my next lecture. Thank you very much.